Welcome to the glass plate. In this example we're going to pretend that we live, like the Inuit, in an igloo. That is, our house looks something like this. A half-spherical dome of radius r in which people live that produce heat. Every person roughly produces 150 watts. The outside is cold, the inside we like to have warm. So there is a delta T, which is in polar areas on the order of 40 degrees Celsius, 20 inside, minus 20 on the outside, that drives heat outside our igloo house. And we would like to analyze in this example with how many people, n, should we be in this igloo such that we don't need to heat with any other means. Only the heat we produce ourselves is sufficient to keep this at 20 degrees Celsius. And we do that for a steady state, obviously. Now the igloo is made of compressed snow, ice bricks, and the thickness of our ice bricks is about 30 centimeters. Hence, in a steady state, we can set up a heat balance which will read that as its steady state is to 0, in minus out plus production should sum up to this 0. Nothing comes in, no heat flow comes in. Out we need to model, and in a steady state this is conduction through a thin layer which we can estimate as lambda times delta T, the driving force, over the thickness of the layer multiplied by the area according to the steady state solution of Fourier's law. And the production is n times the production per person, which is our 150 kilowatts. Okay, now that we've set up the balance and we do know how much flows out and we do know how much is produced, we can back out the rest. The area is the area through which we lose our heat. And just for the sake of the argument, we will neglect all heat that we lose to the floor. Obviously not really true, but the majority is lost via the wind howling around our igloo. So the area is the area of a half sphere, which is 2 pi r squared. And thus, we can write our balance and back out that unknown number that we would like to know. Our balance now reads as 0 equals minus 2 pi r squared for the area times lambda delta T over the thickness plus the production is n times the production per person, 40 degrees Celsius, 30 centimeters. This one is about 0.3 watt per meter Kelvin. R on the order of 2 meters to have a decent house, a decent igloo, so that it's 2 meters high and I can stand. And this was our 150 kilowatt. I wrote here, no way, watt. And thus, from this we have that the number of people you need to keep the inside warm without any additional heating equals lambda 2 pi r squared delta T over delta times the P per person, which is roughly 7 people. That should do to have a comfortable environment inside the igloo without any additional heating.